This video demonstrates our work on learning-based navigation and collision avoidance through reinforcement for UAVs. We propose a learning approach combining reinforcement-based navigation scheme and low-level advanced control for UAV applications. The RL-based navigation is for UAVs in dynamic environments. The navigation scheme is fully autonomous, runs in real time, and solves a non-convex long-horizon prediction task. It incorporates a robust collision avoidance capability to safely guide the UAV through a dynamic environment. To achieve this, the proposed approach puts the RL agent at the top of the control hierarchy, allowing it to focus on behavioral intelligence. In turn, the low-level controller minimizes any unwanted disturbances and model discrepancies, to attain the desired performance of the UAV in flight. The proposed approach is trained purely in simulations, where a simulated UAV is used to navigate to a goal position in a dynamic environment. The velocity of the simulated vehicle closely matches the actions generated by the RL agent. It is essential that such actions do not exhibit oscillatory behavior and hence result in a smooth trajectory. Thousands of samples were used to train the agent to achieve the desired task by exploring various trajectories in the environment, in presence of dynamic and static obstacles. Upon reaching the goal position, the RL agent slows the UAV down, preparing it for landing. We demonstrate the transferability of the RL policy trained in simulation to a real UAV, in a goal-oriented navigation task, without randomization of the system's dynamic parameters. Particularly, the UAV has to smoothly navigate from its initial position to the goal position, while avoiding collisions with the obstacles in the environment. Upon approaching the goal position, the RL agent gradually slows the UAV down, preparing it for landing. Looking closely at this example, the UAV first heads towards the goal and avoids the static obstacle in the middle of the environment. After that, it heads back towards the goal, but it observes the dynamic obstacle approaching. Consequently, the UAV temporarily moves away from the goal to avoid the obstacle. Once the dynamic obstacle drifts away, the UAV is directed towards the goal again. Then, the agent tries to gradually reduce the speed of the UAV to stop at the goal position. In this scenario, the obstacle is moving clockwise. The UAV initially moved clockwise following the obstacle. Then the dynamic obstacle was observed along the way to the goal, and so the agent directed the UAV to reverse direction and approach the goal from the other side. In this case, the obstacle is moving counterclockwise towards the goal. The UAV navigated the environment clockwise from the other side, and then gradually reduced speed to stop at the goal position. Here, the obstacle is also moving counterclockwise, but this time it's heading towards the UAV away from the goal. So the agent directed the UAV to navigate counterclockwise to approach the goal, then smoothly stop at the goal position. Again, in this scenario the UAV navigates towards the goal counterclockwise, then slowly decelerates to stop at the goal. The learned policy exhibited a high level of smoothness when generating actions, as could be observed from the presented simulated and real-time experiments. This is attributed to the formulation of our reward function that penalizes excessive actor actions, in addition to other task-specific rewards and penalties. Without the proposed excessive action penalties, the agent is still able to achieve the task, but without assuring the smoothness of the flight as shown in this example. This is a critical problem that RL-based controllers suffer from, where they generate actions that fluctuate at high frequencies, resulting in undesired aggressive UAV behavior. In this real-world scenario, we show the behavior of the UAV without using our proposed action penalty in the reward term. It is clear that the UAV is struggling to stop at the goal position due to the oscillations in the actions generated by the agent. Our reward formulation solved this problem by penalizing large changes in consecutive actions. The resulting UAV trajectories are smooth, in both simulations and real-world experiments. Our proposed approach achieved a success rate of 90% in real-world experiments.